Stoichiometry, reporting. Gusto ko yan!
Audio Jungle. Audio Jungle. Audio Jungle.
Good day to each and everyone. Today, our group will be discussing stoichiometry, molecular weight calculation, mole concept, and percentage composition. By the end of this lesson, you are tasked to answer a Google Form quiz that will be posted on our Google Classroom. Please listen attentively so you can follow the lecture. Stoichiometry is considered as the mathematics of chemistry, which focuses on the study of the quantitative relationship or ratio between two or more substances undergoing a physical or chemical change. It is used to calculate masses, moles, and percentage of products and reactants within a chemical equation. A German chemist named Jeremias Benjamin Richter was the one that discovered the law of definite proportion, also known as stoichiometry, in 1762. Stoichiometry came from the Greek word stoichion, meaning element, and metron, meaning to measure. Starting with a balanced chemical equation, we make use of proportional nature of chemical reaction to calculate the amount of reactants needed at the start or predict the amount of products that will be produced. It may not seem all that chemical. Stoichiometry is a concept that underlies our ability to understand the impact and implication of many chemical processes. These are the concepts that are important in stoichiometry: balancing equations, converting between grams and moles, calculating molar mass, and calculating molar ratio.
Hi, I am Geneva Idurita and I will be going to report the molecular weight computation. When the topic is the molecular weight, molar mass always comes in, and it's okay because they are really similar to each other. The only difference between the two is the unit that we're going to use. So what is molecular weight computation? It is the sum of the atomic masses of all atoms in a molecule. But before we can get the sum of the atomic masses of the atoms, we need to solve their weight individually using this formula. The formula is the atomic weight of an element times to how many are in that molecule, or in other words, the number of atoms in that molecule. Before we start in the problem, take note that the molecular weight is using the unit AMU or atomic mass unit, while the molar mass uses gram per mole as its unit. Here's the first example. Find the molecular weight of an oxygen. First, let's up this box from the periodic table. It is the element oxygen and you can clearly see here its atomic number. Performing the formula, let's distribute the values. The atomic weight of an oxygen is 15.999 grams or 16 grams. And the number of atoms of oxygen is 2. Multiplying this, we will obtain 32 grams. Now, the molecular weight will end up to be 32 AMU and the molar mass is 32 grams per mole. As you can see, they are the same but different in units. The second example is the water. Let's up these two boxes again. You can see that the hydrogen's atomic weight is 1.008 grams, and in the given, you can see that the water has 2 hydrogens. Multiplying this, we will end up having 2.016 grams of hydrogen in water. Same process on the oxygen. Oxygen has 16 grams, and since oxygen has no subscript, we put 1. Multiplying it will end up having 16 grams of oxygen in water. 2.016 grams plus 16 grams is equals to 32.256 grams. Writing the molecular weight, we have 32.256 AMU and molar mass of 32.256 grams of H2O or water. Move forward to more complicated. I have here aluminum sulfate. The first thing we need to do here is to find the number of atoms of each element. Aluminum has 2, sulfate has 3 because there's a subscript outside the parentheses, meaning you need to multiply it to the subscript of the elements that's in the parentheses. So 1 times 3 is equals to 3. Oxygen, 4 times 3 is equals to 12. Pulling up these boxes again, write down the atomic weight of each element. Aluminum has 26.928 grams times 2 is equals to 56.856 grams. Sulfur has 32.066 grams times 3 is equals to 96.198 grams. And oxygen has 16 grams times 12 is equals to 192 grams. Adding all of these will end up having 345.162 AMU as our molecular weight, and our molar mass is 345.162 grams per mole. Thank you.
In our daily life, we often use words or terminologies that exist for the purpose of representing a number. For example, when we say a pair, we are saying that there are two of something. A pair of socks means that there are two socks. Another terminology that we use to denote a specific number is a dozen. A dozen of eggs means that there are 12 eggs. Now, these words or terminologies are used in matter that we can easily count by our naked eye. But what if we were asked to count the number of particles or atoms within a sock or an egg? Pretty challenging. Or what if we were asked to count the number of atoms within a hydrogen sample? Now again, this is quite challenging, for we know that the number of atoms and the number of particles or the number of molecules within a certain type of matter is very, very large. It's not easy to count. So this is where the mole concept becomes useful and convenient. So now, let's talk about the mole. Well, the mole was first introduced to us by a German chemist named Wilhelm Oswald in around 1896. He derived the terminology from a Latin word moles, which means a heap or a pile. And according to Britannica, a mole is a standard scientific unit used to measure huge quantities of small substances, such as atoms, molecules, and other specified particles. The mole is basically like the terminologies pair and dozen, for it also signifies a number. A huge number at that. Like how a pair is equal to 2 of something, 1 mole is equal to 6.022 times 10 raised to 23. Atoms, molecules, or other specified particles. This large number is called the Avogadro's number. In computation, the number of moles is denoted by a small letter n. The Avogadro's number is denoted by a big letter n with a subscript a. Lastly, the number of elementary entities is denoted by a big letter n. The elementary entities that can be represented in moles could be an atom, a molecule, or other specified particles, such as an electron. These quantities help us arrive to the formula that can be used to solve the number of moles in a given substance. And the formula is the number of moles equals the number of elementary particles all over the Avogadro's number. Let's use this formula, shall we? In this example, we are asked to find the number of moles in a sample of 3.0 times 10 raised to 24 hydrogen atoms. Let us write our formula to better practice it and imprint it in our minds. So we have the number of moles represented by a small letter n equals the number of elementary entities, in this case is an atom and is represented by a big letter n, over the Avogadro's number. So this A is a subscript, as what I have explained a while ago. I just can't write it as a subscript as of this moment because, well, it's hard. Okay, so from the problem, we are given the number of hydrogen atoms, which is our elementary entity. The value of it is 3.0 times 10 raised to 24 atoms. And we're also given the Avogadro's constant, which is, again, 6.022 times 10 raised to 23 atoms. We need to remember this number because we're going to be using this a lot in our lessons. So, notice that I use atoms for the unit of the Avogadro's number. Well, I use the unit atom because it is the elementary entity that the problem has provided. Also, I said that the Avogadro's number is given in this problem, even though we can see it clearly that the only given entity or quantity in this problem is the number of hydrogen atoms. Well, the Avogadro's number is a given because it is a constant. Okay, so we're going to find the number of moles. So now that we have identified what is asked and the given quantities, we can now use the formula to find the number of moles in the given hydrogen atoms. Using the formula, we can find the number of moles. So we are going to find the number of hydrogen atoms, which is 3.0 times 10 raised to 24 atoms, by the Avogadro's constant, which is 6.022 times 10 raised to 23 atoms. So, what do you think is going to be the answer? Use your calculator to find out. I'll give you 3 seconds. 1, 2, 3. Okay, you're done. The answer is 4.9817 moles. For the next problem, we are asked to find the number of atoms in 4 moles of carbon. Again, let's write our formula first. So, the number of moles equals the number of elementary entities, which is, in this case, we're going to find the number of atoms. So, the entities here is the atom, over the Avogadro's constant. So, in this problem, we are given the number of moles, which is 4 moles of carbon. And we are also given the Avogadro's number, which is 6.022 times 10 raised to 23 atoms. And we are going to find the number of carbon atoms in the given sample. Okay, so we can now plug in the given quantities in our formula. So we are given the N, 4 moles of carbon, equals, we don't have the big letter N, which is the elementary entity, which is the atom of the carbon sample. And we are given Avogadro's number. So, in this case, we're going to be manipulating the formula. I'm going to multiply the Avogadro's number in both sides of the equation. In this way, I am going to cancel the Avogadro's number in the right side of the equation, and I'm going to be transferring it to the other side of the equation by multiplying. So, in this, we're going to be multiplying the 4 moles of carbon by the Avogadro's number. This is 23, I'm sorry. In this, we are going to be able to find the number of atoms in the given carbon sample. So, what do you think is going to be the answer? I'll give you 5 seconds this time. 5, 4, 3, 2, and 1. The answer is, by multiplication, 2.4088 times 10 raised to 24 atoms.
Well, here you have it.
Hi, my name is Celia Isabel Roque, the reporter of percent composition of compounds. So, the percent composition compound is the percent by mass of the elements that make up of the compound. The percent composition can be obtained using the formula below. The percent of composition of an element is equal to numbers of atoms of the element times the atomic weight of the element over the formula weight of the substance times 100%. So, for the instance of the mole in the water or H2O, weighs the 18.02 grams, there is a 2 moles of each atoms in the molecule. By multiplying the 1.008 grams by 2, we get 2.016 grams. To get the percentage of hydrogen, divide the 2.016 grams by 18.02 grams and multiply by 100. We know that percentage of hydrogen is 11.19. To get the percentage of oxygen, we divide the 16 grams by 18.02 and multiply the quotient by 100. We then get the 88.79% as the percent composition of oxygen. So that's it. Thank you.
In this video, we're going to calculate percent composition. Percent composition is the percentage of each element present in a pure substance. Let's take a simple problem. Calculate the percent composition by mass of glucose, C6H12O6. The first step is to actually calculate the molar mass of glucose. To do this, we'll look at the carbon, hydrogen, and oxygen and look at the number of moles of each of these elements in the compound. So C6H12O6, we can see that we have these quantities. To get the amounts on each one of these, we're going to need to multiply by their atomic mass in grams per mole. So 12.011 grams per mole. For oxygen, 1.008 grams per mole. And for oxygen, 15.999 grams per mole. The moles will cancel out. We'll end up with 72.066 grams of carbon per mole of glucose. For hydrogen, 12.096 grams of hydrogen per mole of glucose. And for oxygen, 95.994 grams of oxygen per mole of glucose. We can add these three together and we'll get a molar mass of glucose of 180.156 grams per mole. So that gets us molar mass. To get the percent composition, what we'll have to do is look at the mass percentage of each of these elements. For carbon, the mass percent of carbon is going to be equal to the mass of the carbon in glucose, 72.066 grams of carbon per mole of glucose, divided by 180.156 grams per mole of glucose, times, since we want this in percentage, time 100%. For carbon, it'll give us 40.001%. If we do the same calculation for hydrogen, mass percent of hydrogen is going to be equal to the weight of the hydrogen in glucose over the molar mass equals, in this case, times 100%, will equal, in this case, 6.7142%. And finally, if we look at the mass percent for oxygen, we'll have 95.994 grams of oxygen per mole of glucose over the molar mass, 180.156 grams per mole of glucose times 100%. And we will do the calculation. We get 53.284%. So therefore, the percent composition for glucose is going to be 40% carbon, 6.7142% for hydrogen, and 53.284% for oxygen.
In this lesson, we have learned that stoichiometry is the calculation of quantities in a chemical equation. It tells us what quantity of each reactants we need in order to get enough of our desired product. Because of its real-life application in chemical engineering as well as research, stoichiometry is one of the most important and fundamental topics in chemistry. Next is molecular weight, which is the measure of force acting on a molecular mass. It is also the measure of some of the atomic weights, values of atoms in a molecule. We have learned how to calculate the molecular weight. The number of each type of atom is multiplied by its atomic weight and then added to the weight of the other atoms. Mole concept is a convenient method of expressing the amount of a substance. A mole is a standard specific amount of substance containing the same number of discrete entities such as atom, molecules, ions, and etc. The number of entities composing a mole has been experimentally determined to be 6.022 times 10 raised to 23, which is a fundamental constant named Avogadro's number, so denoted as N sub A. To get the number of moles of a substance, the total number of entities in a given sample should be divided to the Avogadro's constant. Mole concept provide a bridge between the atoms and the macroscopic amounts of materials that we work in the laboratory. Last is the percentage composition, which allows us to determine the percentage of each element that makes up a specific compound. To get the percentage composition of an element, multiply the number of atoms of an element by the atomic weight of the element, then divide it to the formula weight of the substance. After getting the quotient, multiply it by 100. Stoichiometry, molecular weight calculation, mole concept, and percentage composition are indispensable concepts for fully understanding any chemical process. Hope you all understand the lesson for today. Thank you and God bless.